Alright guys, so let's talk about the area of a plane region and finding the area using a limit definition. So here's what's going to happen. We're going to have some curve, and I'm just going to draw something generic here. Here's f of x. And we are looking at estimating the area under the curve. Okay, because we haven't gotten to the big deal in calculus, which is called the fundamental theorem of calculus. So let's say we want to find the area from here to here. I'm calling it A to B. We could get a pretty good estimate by looking at rectangles. Let's say we divided this up into maybe 4 rectangles. So we could draw rectangles this way. And you can see this would give us a pretty good estimate of these. So we could use what's called the left sum, and we can use what's called the right sum. So we're going to have a couple of different options here. Your book likes to use lower and upper sums. So when we talk about the lower sum, we're talking about rectangles that are going to be inscribed. Inscribed means inside. So most of these are going to be inside of that rectangle, which means what's going to happen, or inside of the curve. So what's going to happen is this is going to underestimate the area. And then we're going to look at upper sums. So upper sums are areas, we're looking at circumscribed, which means they're going to be on the outside. So this is going to overestimate the area. So let's see if I can draw you a better picture of what's going on. Maybe we just look at something like this. Quadratic. And we're going to go from here, I'll call this A to B. Just those values here. So if we're looking at circumscribed, these rectangles in this case would look like this. Do you see how they're going to overestimate that area by just a teeny little bit if we were to look at 4 rectangles? So that's what we mean by circumscribed. And if we're talking about inscribed, we're talking about being on the inside. So these rectangles, you can see how these would underestimate what's going on here if we were to shade those in. So that's what we mean by being inscribed angles. Most of those are going to lie inside of that figure, so it's going to underestimate what that actual area is. But if we were to take the number of rectangles and instead of doing 4, maybe we did 8. So now that width for that rectangle would be smaller, so then those areas are going to get more precise. So you can see how that's going to change this figure by just a hair here. And we could draw all the rectangles if we really wanted to. So what's going to happen is the more rectangles we create, the closer our area is going to be. So then what this inequality is going to try to say is that we're going to have a lower sum where the rectangles are going to underestimate the area. We're going to have an upper sum where they're going to overestimate the area. So then what's the actual area? Well, the actual area has to be in between whatever those rectangle areas are. So, and that's what this inequality is saying here. They're using S of n to talk about the inscribed and the capital S of n to talk about the circumscribed. So that actual area has to be between that lower sum and that upper sum. So here's a nicer picture than what I drew of inscribed rectangles versus circumscribed rectangles. And looking at limits of upper and lower sums here. And what happens is if we were to take the limit as the number of rectangles goes to infinity, then that lower sum is going to get close to that upper sum. So they're going to kind of come between, and they're going to meet in the middle. And that middle is going to be that exact area. So this process is, think about when we did derivatives by hand and we use that limit definition. This is using the limit definition for integration. And I want to just kind of walk through one, and then we'll get into the fundamental thermocalculus in the next video. I just kind of want to show you where all this is coming from and why we're doing it. So let's look at one example. Let's look at number 29. So we have the function 2x plus 5, and we're going from 0 to 2, and we want to look at 4 rectangles here. So we're going to look at left and right endpoints. So I'm going to call these left and right sums instead of upper and lower. So let's draw a picture. Let's start by drawing a picture of what this guy's going to look like. So we have 2x plus 5. We're going from 0 to 2. If we were to plug 0 in, we would get 5. If we were to plug 2 in, we would get 9. So here's our graph. So let's look at that left sum. So we're talking about 4 rectangles. We've got to split this into 4 rectangles. So we got to figure out how big are the rectangles going to be. How wide. So to figure out how wide, and we're going to call that width delta x, it's going to be b minus a divided by n. Okay, so we're taking that area between here, which is 2 units wide, and we want to divide by how many rectangles we have. So each rectangle is going to be 1/2 of a unit wide. So if we're using left sums, we're starting on the left side of the figure. So that first interval goes from 0 to 1/2. And then we're going to draw that rectangle out. And then we're going to do the same thing here. That graph touches here at 1/2. And then we're going to draw that rectangle out. Same thing here. There's the figure at 1/2. Draw the rectangle out. And then here. And draw the rectangle out. So you can see how these are inside of that graph. Okay. So they are going to underestimate. This happens to be the lower sum because they underestimate. Lower means it's going to underestimate. So let's talk about how to find the area of a rectangle. To find the area of a rectangle, isn't it just length times width? So what we're going to do is we're going to find the area of 4 rectangles, and then we're going to add them all together. So to find this area, it's length times width for each one. So the length is 1/2. So now we need to find the width. So the width would be, in this case, or we could think about it as a height. How tall is this rectangle? How far does it go up? Well, that height is really based on that equation, 2x plus 5. So if we were to take that equation and we were to substitute in 0, because we're using the left side of each of those intervals, then that's going to give us the height. So it's going to width times the height. We're going to do the same thing for the next one. The width is 1/2. That height of this rectangle is based on the left side of that interval. So our left side for the first one was at 0. The left side of the second one is 1/2. And then we're going to do the same thing for that next rectangle. It has a width of 1/2. The height is based on the left side of this interval. And the left side is at 1. So we need to find how tall is that function at 1. And then we're going to do the same thing over here. The interval is between 3/2, or 1.5 and 2. The left side is at 3/2. So this is finding the area of the first rectangle, second, third, and fourth. If we were to substitute 0 in here, we're going to get 5. So that height of that first rectangle is at 5. We're going to do the same thing for the next one. If we were to substitute in 1/2, we're going to get 6. If we were to substitute in 1 into our equation, we're going to get 7. And if we substitute in 3/2, we're going to get 8. So if we were to add all these together, we're going to get 13. So that left sum, and I'm going to use an AL to let us know that that's the left sum, is 13. Now keep in mind, this is going to underestimate because those rectangles aren't going quite up to that line. Now let's talk about the right sum. I'm going to change my color here. So when we talk about the right sums, we're talking about using the right endpoint to draw this rectangle for each one. So the width's going to be the same because we're still using 4 rectangles. But instead of starting at 0 and drawing the rectangle, we're using the right side. So we're starting at 1/2. So then our first rectangle will look like that. That second rectangle is going to use the right side. So it's going to use that 1. It's going to go up to the graph. And then it's going to draw that. The third rectangle would go up to the graph, starting with x equals 3/2, and then draw. And then same thing here. We're going to go up to 2 and draw. So you can see how these rectangles are going to overestimate that actual area. So that's what they mean by an upper sum. Upper just means that it's going to overestimate what's going on with that area. So if we're looking at that right sum, I'm going to use AR. The width is still 1/2, but our heights have changed a little bit. That first rectangle, to find that height, we use the right-hand side of that interval, and that right-hand side is 1/2. For that second interval, which is between 1/2 and 1, that right-hand side is 1. For that third interval, we're between 1 and 3/2. We're going to choose the right side, 3/2. And then for that last triangle, or rectangle, last rectangle, this is the fourth one, we're going to use that side of 2, since that's the right-hand side of that interval. So the width for each one is 1/2, but we need to substitute 1/2 into the function to figure out how tall or how wide that rectangle is. So if we plug 1/2 in, we're going to get 6. If we substitute 1 in, we're going to get 7. If we substitute 1.5 in, we're going to get 8. And if we substitute 2 in, we're going to get 9. So if we add all that together, we're going to get 15. So we've underestimated with the 13. We've overestimated with the 15. The actual area has to be some number between those. Now, if we were to change the number of rectangles, instead of doing 4, maybe we decided to do 8, then these would actually become better estimates, and it would give us a more accurate idea as to where that actual area would lie between. But right now, we're just talking about how can we get close to that area. And we'll see coming up that we can use a limit definition to help us figure out what the actual area is going to be.